A diversity index is a quantitative measure that reflects how many different types there are in a dataset, and simultaneously takes into account how evenly the basic entities are distributed among those types. The value of a diversity index increases both when the number of types increases and when evenness increases. For a given number of types, the value of a diversity index is maximized when all types are equally abundant. When diversity indices are used in ecology, the types of interest are usually species, but they can also be other categories, such as genera, families, functional types or haplotypes. The entities of interest are usually individual plants or animals, and the measure of abundance can be, for example, number of individuals, biomass or coverage. In demography, the entities of interest can be people, and the types of interest various demographic groups. In information science, the entities can be characters and the types the different letters of the alphabet. The most commonly used diversity indices are simple transformations of the effective number of types, but each diversity index can also be interpreted in its own right as a measure corresponding to some real phenomenon. True diversity, or the effective number of types, refers to the number of equally abundant types needed for the average proportional abundance of the types to equal that observed in the data set of interest. The true diversity in a dataset is calculated by first taking the weighted generalized mean MQA1 of the proportional abundances of the types in the dataset, and then taking the reciprocal of this. The equation is: the denominator MQA1 equals the average proportional abundance of the types in the dataset as calculated with the weighted generalized mean with exponent Q1. In the equation, R is richness, and the proportional abundance of the ith type is pi. The proportional abundances themselves are used as the nominal weights. When Q equals 1, the above equation is undefined. However, the mathematical limit as Q approaches 1 is well defined and the corresponding diversity is calculated with the following equation, which is the exponential of the Shannon entropy calculated with natural logarithms. The value of Q is often referred to as the order of the diversity. It defines the sensitivity of the diversity value to rare versus abundant species by modifying how the weighted mean of the species' proportional abundances is calculated. With some values of the parameter Q, the value of MQA1 assumes familiar kinds of weighted mean as special cases. In particular, Q equals 0 corresponds to the weighted harmonic mean, Q equals 1 to the weighted geometric mean and Q equals 2 to the weighted arithmetic mean. As Q approaches infinity, the weighted generalized mean with exponent QA1 approaches the maximum pi value, which is the proportional abundance of the most abundant species in the dataset. Generally, increasing the value of Q increases the effective weight given to the most abundant species. This leads to obtaining a larger MQA1 value and a smaller true diversity value with increasing Q. When Q equals 1, the weighted geometric mean of the pi values is used, and each species is exactly weighted by its proportional abundance. When Q greater than 1, the weight given to abundant species is exaggerated, and when Q